Okay. Hello, everybody. I hope that you are all doing well. And thank you to Jeremy and Peter for allowing me to speak. Okay, so today I'm going to talk about the categorical graph minor theorem. So let us recall something that I think we all know. So recall. So the category of finitely generated phi modules is abelian, which is just a super fancy way of saying, i.e., Fi modules. I guess if I wanted to be careful here over an Noetherian ring, satisfy the Noetherian property. So I don't think I have to go too much into detail considering my audience here. But one thing that, a perspective that I guess that maybe not everybody is completely familiar with, is the fact that is this perspective of Sam Snowden. Kind of the Grubner perspective. Which essentially says that we can think of this result as a categorification of Higman's lemma. I believe Higman has two, right? So Higman's lemma, for those who don't know, is a statement about Noetherianity for certain posets. Specifically, it's like if you take an Noetherian poset and then look at the kind of subsequence poset on that poset, that thing is Noetherian. So it becomes a natural question. There are many generalizations of Higman's lemma. Can Sam Snowden's kind of Grubner perspective be used to prove Noetherianity results for representations of categories which are somehow categorifying these generalizations of Higman's lemma? In particular, two kind of famous generalizations of Higman's lemma are Kruskal's tree theorem so this is the statement that trees are kind of well-ordered with respect to the contraction order. So you say one tree is less than another if you can contract the bigger one to get to the smaller one, contract edges. And so it turns out that there are no infinite antichains on this order. That's Kruskal's tree theorem. And even more general than Kruskal's tree theorem is the graph minor theorem, which in some respects is one of the kind of maybe greatest achievements in combinatorics ever. So this says the following. This says that if the category, or maybe category, maybe not the best word here. So maybe I should get rid of that as well. Graphs are kind of quasi well-ordered by deletions and contractions, e.g., or i.e., the minor order is a Q W. All right. So for those of you unfamiliar with the terminology, let me just give you kind of the like TLDR version of this. It says that if you take any infinite collection of graphs, so GI, there is some kind of I less than J such that GI is obtained from GJ by a sequence of edge deletions and contractions. So here when I say a contraction, I literally mean you have your edge and then you just kind of collapse it. You identify the two endpoints and just remove the edge. So this is the graph minor theorem. It was proven by Robertson and Seymour in a sequence of 20 papers proven over 20 years. It is really one of the, as I said, one of the pinnacles of combinatorial mathematics. And it, just like Kruskal's tree theorem, in fact, is a generalization of the much simpler Higmann's lemma. So it becomes a natural question to ask, are there categories which kind of categorify these two statements in a similar way that Higmann's lemma was categorified by Fi? And so that brings me to my next definition, G. So this is what we call the graph minor category, defined by Nick Proudfoot and myself. And the objects of G are just finite connected graphs. Whereas the morphisms are what are called minor morphisms. So what is a minor morphism? So this is something that Nick and I define. They're essentially maps between the combinatorics of the two graphs, which satisfy a list of combinatorial properties. In a 20-minute talk like this, it's actually maybe a bit foolish for me to explicitly tell you what those conditions are, but let me just kind of give you the summary here. The idea just probably suffices to note that there exists a morphism say phi from G to G prime, if and only if G prime can be obtained from G by a sequence of edge deletions contractions and graph automorphisms. Yeah, so as I said, like part of the difficulty of this project was in fact defining the category and getting these minor morphisms correct took quite a bit of work. There's a lot of kind of intricate combinatorics involved, but kind of it suffices to say the way you want to think about this is that there exists a morphism from G to G prime if and only if G prime can be obtained from G by a sequence of edge deletions, contractions, and graph automorphisms. Okay, so now that we have the graph minor category, the next thing I want to state is kind of the main theorem. This is due to Proudfoot, Miyata, and myself. And the theorem says that the category of G op modules satisfies a Noetherian property. So this is what I would call the categorical or categorified graph minor theorem. So just as with Fi, the category of G op modules satisfies a Noetherian property. So let me state some corollaries to this. So the following categories satisfy a Noetherian property. In their representations. So, well, Fi, Fs op, Vi Fq, and what I'm going to call G sub G op. This last one is probably the only one I need to explicitly define. This is something, this is the contraction category of graphs with first Betti number equal to G. Okay, so we, in a sense, recover almost all of the representation, like the Noetherianity statements that have thus far been proven using the Snowden-Grubner methods. We recover all of them as consequences of the Noetherianity of G op modules. And morally speaking, this is because, like, in some sense, the graph minor theorem is like the most general graph poset Noetherianity theorem like that can possibly exist. And so all of these kind of follow from the fact that G op modules satisfy this Noetherian property. You know, great. Of course, like all of this is just kind of, I don't know, cute little algebra, unless you have interesting applications. And so let's get into that. So insofar as applications are concerned, for a graph G, we can talk about its configuration space. Fng. So this is unordered configuration space for now on G. A graph is just a one-dimensional CW complex, so it of course makes sense to talk about its configuration space. And as a fact, a minor morphism say 5 G to G prime induces a map on homology of graph configuration spaces, but going in kind of the opposite direction. So this is a fact that was observed by Knudsen, Drummond, Cole, and On. And this is somewhat remarkable because, of course, deletions, unsurprisingly, will induce maps. But contractions, I mean, you would think that that would be counter to the purpose of configuration space. If I'm colliding edges into each other, you would expect points to collide as well. But indeed, we do get maps on homology at the level of homology. Of course, now that I have an induced contravariance on minor morphisms, you can ask, like, oh, wait a minute, are these things G-op modules, and are they finitely generated? And indeed, that is kind of the main theorem. It states that the G-op module G maps to HI Fn of G is finitely generated. For all I and n. Okay. So unlike in the case of configuration spaces of, say, manifolds, where representation stability takes the form of alter the number of points, but the manifold stays fixed, somehow it turned out that in graph theory, or rather for graph configuration spaces, it was much more natural to fix the number of points being configured and allow the graph itself to alter in some way. And this was kind of a line of research that was done by myself and Daniel Luca Hetman and others. And somehow this result is in fact the culmination. All results about stability of graph configuration spaces, specifically in the regime of fixing number of points and altering the graph, are consequences of this more general theorem. Now, of course, it's disappointing, like that we have to fix n, and so is there a way that we can get similar results while allowing n to vary? And the answer is yes. So moreover, there's a version of this theorem where only I is fixed. It's considerably more difficult to state because there's two actions happening, the action of changing this and the action of changing the graph. And the point is like you can make these two actions compatible, but that's probably more detail than I'll have time to go into. So in particular, as a corollary to kind of this moreover, we can recover the fact that the kinds of torsion which can appear in the homology of graph configuration spaces only depends on the homological index. So this was something that was in some sense observed 20 years ago. There was a result that said that H1 of graph configuration space can detect planarity of the graph, and it does so by basically you look at H1 and you ask, do I have torsion? And the answer is like, if I have torsion, the torsion is only ever two torsion, and it's detecting it's detecting the lack of planarity if I have torsion. And so this corollary here, this fact that the torsion across all graphs of that the torsion in graph configuration space is like absolutely bounded, what shadows of it were observed before, but this result in fact is somehow a unifying force, which is saying that the reason for this boundedness is very, very deep and in some sense related to this graph minor theorem and this stability coming from the graph minor theorem. Yeah, so that's all I have. I'll have time for now. I look forward to any questions or whatever, just shoot me an email. Yeah, so thank you for your time, and yeah, I hope to see you all in person soon. Okay, bye-bye.